Greetings everyone. So today we are going to discuss about the elevation of boiling point. As a result of the colligative properties, we saw that there was lowering of vapor pressure according to Raoult's law. But if we consider the lowering of vapor pressure, if a vapor pressure of a solution is lowered, let's suppose the solution is a solution whose vapor pressure is lowered at a constant atmospheric pressure. At a constant atmospheric pressure, if the vapor pressure of a solution is lowered, then this causes to increase the amount of effort which is required to in to reach the vapor pressure equal to the atmospheric pressure, right? Such that if this is what we consider, let's suppose if this is where we our solution will start boiling, then if the vapor pressure is lowered, if the vapor pressure is lowered to this extent, if the vapor pressure is lowered to this extent, then at that moment the amount of effort which is required by the vapor pressure in order to achieve the vapor pressure equal to the atmospheric pressure is increased, which is represented by this graph, as a result of which we can say that there can be a high difference between the uh, boiling point of the pure solvent and the solution due to difference in the amount of vapor pressure which is required to become equal to the atmospheric pressure of the solvent than the atmospheric pressure of the solution, due to which we can say that here this difference in boiling point can be considered as an elevation of the boiling point, as a result of which this difference is considered to be an elevation of boiling point, and that elevation of boiling point is represented by the graph given here. As you can see, if we talk about solvent, let's suppose this is a graph where AB represents the curve of solvent and CD represents the curve of solution, and this is a point where the solution will start boiling, solution or solvent will start boiling, right? So when it comes to AB or the solvent will start boiling when the vapor pressure is coming till here. But when it comes to CD will start boiling when the vapor pressure will come over here. Vapor pressure will come over here, due to which we can say that as the vapor pressure is lowered, the all right, there's a mistake. So CD will start boiling when the vapor pressure and atmospheric pressure would be equal. The atmospheric pressure which is here would be equal to the point at the curve CD. So in order to make vapor pressure equal to CD, there should be a higher vapor pressure required in order to achieve the boiling point, due to which we can say that there is an elevation in the boiling point due to the increase in temperature which is required to increase the vapor pressure becoming equalized to the atmospheric pressure of the solution, as a result of which the solution here will have an elevated boiling point as compared to its pure solvent, as a result of which we can say that this elevation in boiling point is considered as a colligative property which is dependent on the number of particles but not on the structure of the particles. So this is what we consider in the elevation of boiling point. And when it comes to its mathematical derivation, we can say that here uh, the elevation is boiling point represented by delta TB is equals to T1, or in the terminology of a book, TB minus TB naught. TB naught is the boiling point of vapor of the solvent and TB is the boiling point of solution. So we would be considering TB minus TB naught. right? Now, it has been experimentally proved that the elevation in boiling point is directly proportional to the molal to the amount number of moles of the solution, directly proportional to number of molar solution, due to which molality, it is directly proportional to the molality of the solution, due to which when we are going to remove the proportionality sign, we'll add a constant over here, which is known as the molar boiling point constant, molar elevation constant, or ebullioscopic constant, which is known as Kb. And this constant basically is only dependent on the nature of the solvent, but not dependent on the nature of solute until the solute is not ionized, because if the solute is ionized, it will start to form forces of attraction between the solvent particles or the solutions particles, due to which it will cause to show difference in the rate of evaporation and condensation, ultimately a difference in the vapor pressure, and ultimately a difference in the boiling point of the solution, due to which unless it is not ionized, it has the solute nature does not have any influence, right? And this is about it. And when it comes to a 1 molar solution, whenever we are having a solution in which 1 mole of a solute is dissolved in 1 kilogram of the solvent, then delta TB, or elevation in boiling point, is equals to Kb into 1, because molality of that solution would be 1, due to which we can say that delta TB is equals to Kb. At that moment, we consider the elevation in boiling point equal to the ebullioscopic constant, and ebullioscopic constant for water is 0.52, such that uh, for 1 molar solution of water, 1 molar solution of a solute in water, the boiling point elevation would be 0.52 centigrade. And if we take 0.1 mole solution, 0.1 molar solution in water, then uh, we can divide 0.52 by 10, then whatever the answer would be, it would be considered uh, as the amount of elevation in the boiling point, which would be equal to 0.052. So this is how we consider it. And when it comes to the depression and freezing point, it is a characteristic in which we have a depression in the freezing point of the substance, such that we know that whenever a solid phase of a solution, whenever solid and liquid phase of a solution or solvent or a liquid exist in equilibrium with each other, then this condition is known as freezing point. Or in a condition in which the melting and freezing, in which melting and freezing occur in equilibrium, are known as the freezing point, right? And here, as you can see, whenever we are having lowering in vapor pressure causes the vapor pressure to be decreased, as a result of which the rate of condensation is ultimately decreased, as a result of which the rate of evaporation is decreased, as a result of which decrease in rate of condensation and evaporation causes a decrease in the rate of melting and freezing as well, as a result of which, as a result of the decrease in the rate of melting and freezing, there is depression in the freezing point, right? And as a result of that depression and freezing point, we can consider here the graphical representation of this depression and freezing point by the following graph. Let's suppose this is a graph again, D E C, and this is a graph D B sorry DTC, let's suppose, right? Now, BEC represents BETC represents the liquid solvent, and DTC represents the solution. Now here, the solvent basically from B to E represents the liquid state, and from E to C represents the frozen solvent state or the solid state. Now, E is the point where the liquid and solid exist in equilibrium with each other, or we can also consider point E as the freezing point of the solvent, right? But when it comes to the freezing point of the solution, freezing point of the solution is occurring at the point T, right? Due to which we can say that freezing point of the solution is at T, which is less than the freezing point of the solvent, due to which we can say that the depression in freezing point occurs whenever there is formation of a solution as a result of lowering in vapor pressure. Now, if we come to mathematically derive it, we can say that here delta TF, depression in freezing point, uh, is directly proportional. First, we need to understand its terminology, that here we can simply write it as delta TF is equals to TF minus TF naught, TF minus TF naught, right? This is what we consider as depression in freezing point, which is the difference between the freezing point of the solvent and the solution. Delta TF is directly proportional to molar solution, experimentally proved, after which delta TF is equals to, whenever we are removing the proportionality sign, we let a proportionality constant which would be added over here, which is known as Kf, and that Kf is the molar freezing point constant, molar depression constant, or the cryoscopic constant. Again, it is dependent on the nature of the solvent and not dependent on nature of the solute, because nature of the solute does not play a vital role unless it is not ionized. If it is ionized, then forces of attraction will be formed, which will lead to you know ionization, and alter the rate of vapor pressure and alter the freezing point ultimately, due to which Kf is only dependent on nature of solvent. Now Tf and M are in a direct relation with each other, apart from which whenever there is one molar solution in which 1 mole of solute is dissolved in 1 kilogram of solvent, we are going to utilize we are going to consider the depression and freezing point equal to the cryoscopic constant. Depression and freezing point equal to the cryoscopic constant. Apart from which, when it comes to water, for water the depression and freezing point is around 1.86 centigrade. If we are taking if we are taking 0.5 molar solution of water, 0.5 molar solution of any compound in water, so at that moment we are going to divide it by 2, due to which whatever the answer would be, we'll be just writing it. It would be what I believe it would be 0.93 something. So 0.93 centigrade would be the depression in the freezing point. And depression in freezing point is quite useful because there are certain applications in daily life, such that in car radiators we utilize antifreeze, which is ethylene glycol. Ethylene glycol is an antifreeze in car radiators, which is responsible for both decreasing the freezing point, depression of freezing point, as well as increasing the boiling point of water which is present in the car radiator, right? Such that in cold weather, whenever there's cold weather, the depression and freezing point prevents the water from being freezed in the car radiator. And when it comes to the summer season, in summer season, whenever there's too hot, the increase in the boiling point causes the water present in the radiator to absorb more amount of heat in hot weather, due to which it prevents the radiator from being overheated in case of summer season, as a result of which it is useful in terms of protecting the radiator. Apart from which, whenever we are having ice cream machines, in ice cream machines we are utilizing some salts which show negative deviation from the Raoult's law, such as sodium chloride, sodium nitrate are salts which show negative deviation from the Raoult's law, which have higher vapor pressure, and which basically cause to give higher vapor pressure and lower boiling point, due to which whenever these salts are utilized, these salts are utilized in this process, as a result of which they cause the solute and solvent added within the ice cream machine, which are in this case the milk as the solvent, and sugar and other such ingredients as solute added in the machine, will cause to form a freezing mixture, which would be in uh, the form of a freezing mixture, and that freezing mixture would be having a depression in its freezing point. There would be a depression in the freezing point of that freezing mixture, depression in the freezing point in the freezing mixture, right? Depression in the freezing point of the freezing mixture as a result of the NaCl and sodium nitrate. Sorry, there won't be a depression of the melting point will be occurring because they show a negative deviation from Raoult's law. So depression of melting point will occur and elevation of freezing point will occur, as a result of which the freezing mixture would be having higher freezing point, lower melting point, due to which the ice cream would be made more conveniently even when there is hot weather in an ice cream machine. So this is how the mechanism of ice cream machine works as well. Moreover, whenever we are boiling an egg, so while boiling an egg we basically add some salt in it. Adding salt causes to elevate the boiling point of water, as a result of which the water acquires more amount of heat, due to which the egg is boiled more quickly in case of addition of salt. So these are some common applications about it. Hopefully we'll meet again in another video.